seen that loss function is a very important concept in artificial neural network. Okay, in overall in machine learning itself, it's a very important concept. But sometimes loss functions are also called cost function or error function. But some people do not agree with that. So they say the cost is like all the loss you can add up, and that becomes the cost. And there are different opinions, but in general, loss, cost, and error are considered as the same thing. Okay, so we have already seen our example of the neural network that what is the loss? So when we at the output layer of the neural network, let's say whatever we the output coming out, so let's say that's a predicted y1 prime, y2 prime, and y3 prime, and then we know the what should be the the actual values. Then we try to find out the differences of the given the ground truth and the predicted values, and then we see that we say, okay, that's the difference is the error or the loss or the cost, or whatever you say. So we have so far have used mean squared error, but now let's talk a little more about the different types of loss functions. So there are loss functions are mainly divided in two parts. One is the loss functions which are very good for regression tasks, and loss functions which are good for classification tasks. So here we first talk about the loss function for the regression task, and the first thing is again the same, the mean squared error, okay, which is very good for regression type of tasks. So this is now we have already seen that multiple times, is the average of the differences. Okay, so this is the actual value in the training data, and this is the predicted value. So we find the difference like we did in linear regression and other cases. And then we average it. Okay, so it's the average of the squared error. Okay, so you see there is one thing, this is squared. So if the difference between the predicted value and the actual value are large, then the square of it will be larger. Okay, so that is a problem. So so if it is very sensitive to outliers, okay, when the difference between the predicted and the real value is large, this function kind of pronounces the error more. But this has some good points also. Okay, the good points are that it's a convex function. So convex function, if you remember, it's a function, let's say like a parabola, where if you take any 2 points on the function and you can connect them, this line will be definitely above the function line. Okay, so it's differentiable. So it has a well-defined global minima. Okay, it's a well-defined global minima. And if you remember, in the back propagation, you have to take derivatives, partial derivatives, and to have a convex function and a well-defined global minima is very important for that. We said that it has to be, there should be a derivative, so it's differentiable, so it's good. So that's the good part. The bad part is that it's very sensitive to outliers, pronounces the outlier very large. But how to do that? Then we want to, kind of check with just a mean absolute error. Mean absolute error means only we will not take the square, okay, but we will take the absolute value. This is the absolute value between the actual output and the predicted output, okay. So actual means the training data, whatever it suggests should be the output, and the predicted output. And the difference, I take the absolute value and then take the average over it. So you can see the good part of it is that it's not squared. So the difference is not, the loss is not being double or pronounced. But there's a problem of that. When this, this is like the gap is going to 0, that means the predicted value comes very close to the actual value, then MAE kind of tends to 0. And at that point, you cannot take a derivative. It will be undefined at 0, okay? So the derivative fails. So you cannot apply gradient descent on it. See, that's a back propagation will fail. So that is a problem here. So here you see the error is becoming bigger, but the function is differentiable and its gradient descent is applicable. But here error, for outlier, it handles better because it doesn't square. But when the error is too small, it grows into 0, and then gradient descent will not work. So we have to take best of both worlds. Okay, we have to say, okay, when the outliers are large, then we will do, that means the MAE is pretty large, we will use MAE. And when the there are not many outliers, then we will use mean square error. It's something like, let's say we have a graph like this, and we are saying, okay, so when the error is too much, we use this part, we can use MAE, and when also this part. But when we are coming close to the global minima, that time we use MSE. So these two values are like the thresholds, okay, thresholds above which we will use MAE and below which we'll use MSE, okay, threshold in both directions. So there is a new loss function which is called Huber loss. Okay, Huber loss, what does it do? It does exactly same thing. Huber loss says you use MSE. You see, this is the MSE mean squared error formula, which only a half a constant added. When you take the derivative, the 2 will come down and it will be cancelled. It has no much effect. So when the outliers are not that much, that means that the actual value and the predicted value, the difference is upper bounded by delta, you use MSE. Okay, exactly this. That means the outliers are too little, close to the global minima, use MSE. But if the outliers are high, then use MAE. What it does, it actually multiplies with delta and then subtract half delta with it. And this is the mean absolute error part, and take the average over it. So this is kind of robust to outliers. This tackles both the problems. So this is like best of both worlds. So it's robust to outliers, but the problem also is that you have a new hyperparameter now to tune. You have to find out the best value of delta above which you can use MAE and below which you can use MSE. So you have to tune the value of delta so that you can reduce the error in the regression task. And now we will talk about the classification error.